All right, I'm going to go ahead and start and let people wander in. So we're extremely happy to have Nathaniel Craig visiting us from a much warmer climate than here. Coming from California, from Santa Barbara. He's a theoreticalist. You might get the impression from this that he's all about colliders, but actually he has this whole other side of him where he's speaking entirely in indices. He's had a lot of very influential work thinking about quantum field theories and symmetries of quantum field theory. He's really currently pushing forward many new ideas and trying to take the idea of generalized symmetries and push them into particle physics. That's not what you're going to hear about today. He got his PhD at Stanford for coming to New Jersey, where he was at the Institute and at Rutgers as a postdoc for 4 years before taking his faculty position at UCSB, and he's been there since then. So let's see, he's got DOE Early Career Award, a Cottrell Scholar Award. He got a Buchalter Cosmology Prize, which he used, I've learned, to buy a coffee machine, and was a Blavatnik finalist, as well as many other things. He's currently the head of the Particle Theory Initiative at KTP. But importantly, he's like one of the big people in the United States thinking about what the future of high energy particle physics might look like in the United States. And is in a, well, I won't oversell him, but he's going to tell you about that. And also, we are getting his last Colloquium for some time. He's going on Colloquium sabbatical, he told me. So, yes. So.
Okay, thanks very much, Neil. Well, thanks very much for having me. It's a tremendous pleasure to be here. Indeed, I am going on Colloquium sabbatical. Something Neil didn't mention is I'm also a dad, and my youngest child has recently expressed his unhappiness at my work travel. So I decided to say no to everything else after this, but it's a pleasure to have this be the last Colloquium I give for a while before taking a break. Great, well, thanks very much for being here. Normally when I give a Colloquium, it's helpful to me to get a sense of the audience before I get going. So if you'll bear with me for a second, just by some shows of hands. So how many people in the audience are from astro-cosmo backgrounds? All right, okay, AMO? Condensed matter? Great. Soft and living matter? High energy? Kind of nuclear? It's not so much here. Anything else I missed? Particle department I missed? Okay, that's great. Well, thanks. It's the best colloquium audiences, of course, the ones that are very broad, and this talk is aimed at everybody, so I hope everyone will feel involved. Those of you who do particle theory, if there's some things you know, enjoy that warm feeling, but hopefully I will also say some things that you don't. The other question I have for you, so if any undergraduates in the audience? Okay, I guess they're all over. All right, welcome. Graduate students? Great. Postdocs? Faculty? All right, awesome. This is a great thanks very much again for having me. So indeed, the title of my talk is the Who Ordered That Collider. So as we'll see, of course, Who Ordered That is doing double work here. It is a reference to muons and muon colliders, but it's also sort of the question of who ordered that collider, why it is that we would want to build any colliders beyond the outstanding ones we already have. And to get us started, the background of this image actually comes from the cover of a recent National Academies report. So of course, one of the great functions of the National Academies is to provide expert input to the federal government in the priorities of different scientific fields. And so last year, they completed a long-running panel in elementary particle physics asking about the future of particle physics in the US. And the primary recommendation that came out of this report was to build a US-based muon collider. In particular, in the middle of the century, the middle of the 21st century, the United States should build the world's highest energy elementary particle collider, and in particular that it should be a muon collider as necessary to address the most profound questions in particle physics. And so, if this is the punchline, then what I'd like this talk to be about is in the immortal words of the talking heads. You may ask yourself, how did I get here? Okay, how is it that this was the conclusion of this panel? How is this actually playing into what the future of particle physics in the US looks like? But also more importantly, why is this actually what was deemed to be an appropriate choice for the future of the field? And so that's what I want to tell you about in the rest of the afternoon. So to do that, how did I get here? If you'll forgive me, I want to actually go a long ways back to 1935, and I promise there's a purpose for going all the way back. And just to ask you asked, what was it like to be a particle physicist in some sense before this was even a field in 1935, what did the universe look like? Well, at the time, right, the fundamental description of nature was basically the description of what we thought were the elementary ingredients that made up the universe around us that were necessary for our existence, right? So we knew about protons, neutrons, electrons, things that made up atoms, and we knew about the photon. And this was a great picture because it explained, it seemed like there were all the ingredients that we saw in nature were the ones that were necessary to actually create the universe that we saw. But then something surprising started to happen, right? So in the spirit of scientific inquiry, scientists started building more and more interesting devices. This was actually the turn of the 20th century, building increasingly sensitive electrometers. And the way, of course, if you remember from your undergraduate labs that these work is it's a pair of foil leaves that you might charge up, and then if you expose it to radiation, they discharge and the leaves come back together. And they saw that as they were discovering the phenomenon of radioactivity, that near the Earth, that these could discharge very quickly because of radioactivity. And the hypothesis was, as you took them off the surface of the Earth, away from radioactive sources, the rate of discharge would slow. But then the opposite happened, right? They took these up in hot air balloons, and they discovered that the rate of discharge of these foils actually increased. And that, as we now know, was the discovery of an extraordinary phenomenon, which is the cosmic ray showers. That, of course, the Earth is being bombarded by very high energy particles that create showers of interesting things, and that this was responsible for the elevated discharge rate of these electrometers. And so, as sensible scientists, right, what happened? Well, then we started to ask ourselves, if there are these, at the time, the highest energy experimentally testable phenomenon in nature, we should go ahead and instrument them and see actually what we can learn from them. And so, an increasingly sensitive set of different types of detectors, including bubble chambers and cloud chambers, were put in high altitude parts all around the world, including the top of Pikes Peak. And so famously, Carl Anderson and Seth Nettermeyer, in their observations of the products of cosmic ray showers, discovered evidence for a track whose charge to mass ratio was anomalous with respect to all of the particles that they knew about. And of course, this was then the discovery of a new fundamental degree of freedom, which was the muon. And so, if we just leap forward from 1935 to 1937, suddenly there is a new ingredient in sort of the fundamental description of nature. Famously, Isra Rabi was purported to have said upon the announcement of the discovery of the muon, who ordered that? And the reason for that statement, right, is that everything else that was known up to the time was a necessary ingredient for the universe around us that we saw. And here was something that was absolutely not necessary in any way, right? It was unstable, it decayed extremely quickly. We didn't even know about it until we started to look up at cosmic rays, but it was an important ingredient in the fundamental theory of nature. And this is a takeaway message that has lived with us ever since and lives with us today, which is that you may think you have a complete description of nature, all of the ingredients that you need for a consistent picture, but nature doesn't really care, right? There are many things in nature that seem superfluous to our needs, and the only way to find them is to go about exploring. Right? So already this lesson was given to us very strongly in the 1930s. So then what did we start doing? Of course, we started trying to mimic nature in the laboratory. We realized we could accelerate elementary particles and composite particles to higher and higher energies, smash them together, and reproduce the successes that we saw in cosmic rays. And then there was, basically what followed were decades of extraordinary successes in our understanding of the fundamental theory of nature. And there were sort of two core ideas, which I'll lean on for the rest of the talk, which especially for those of you who don't think about high energy physics on a daily basis, are really all you need to orient yourself in the space of ideas that we'll talk about for the rest of the afternoon. So one of them is something that we became very abundantly clear in this exercise of smashing things together, is that particle physics is a form of alchemy, right? So the alchemists, centuries ago, wanted to transmute some elements into other elements. We know that that was somewhat foolish in their framing, but now we know that we can do it in different ways. The way the alchemy happens in particle physics, right, we like to draw, physical processes as space-time diagrams. So for example, this would be the scattering of two particles off of each other by the exchange of a force carrier like a photon. But loosely speaking, right, special relativity tells you I can turn this diagram on its side. And so if this sort of interaction exists in my fundamental theory, then there's also an interaction where I can take a particle and its antiparticle, annihilate them into some force carrier, and then produce something entirely new. So that's the form of alchemy. And the only price you have to pay to do it is the energy of the colliding particles needs to exceed the rest mass of the things that you want to make. And so this, this has really been the engine of discovery in particle physics for the decades that followed. There was a second idea, of course, that came together as we started studying fundamental particles at higher and higher energies, which is that we learned that the important things in nature are not the particles themselves, but actually they're just excitations of things that suffuse all of space and time. So these are things we call fields. They are, of course, familiar to us even from classical electromagnetism. And the idea in the quantum setting is just that the particles that we smash into each other are really just localized excitations of these fundamental objects. And so I'll pass back and forth between talking about particles and fields throughout the rest of the talk, but this is all that I need. Okay, so starting in the late 1930s, starting with the development of the first cyclotrons, particle accelerators, we started to smash things together at higher and higher energies and pursue this program of alchemy. And I want to fast forward now, about 50 years to 1984 and see where we were in 1984. And the reason I picked 1984, this was shortly after I was born, but that has nothing to do with it, is actually that this was, in 1984, there was a workshop in Lausanne and Geneva that was basically focused on the question at the time. They were constructing and operating an electron-positron collider, LEP, under the Swiss-French border. And the question was, once in somewhat distant future, that collider had reached the end of its useful lifetime, the question was, what do we build afterwards? And this conversation that started in 1984 ended up concluding that to proceed with the construction of the Large Hadron Collider, which is the experiment that we're, of course, still operating in the same time. But the reason I wanted to pause this here is it's really interesting to go back at this document and actually look at the rationale that was provided in 1984, given where they stood for the construction of this futuristic machine that we are now doing science with. And the reason why this is particularly relevant is, if you think about the timelines, as I'll explore later in the talk, we need to be having the conversation now about the sort of collider that will succeed the LHC, in the same way that even though the LHC didn't start collisions until the 2000s, the conversation had to be very concrete in the 1980s. Okay, so where were they in 1984? Well, again, there had been a succession of higher and higher energy particle accelerators and colliders. Here I've just summarized a couple of accelerator facilities. The blue ones are lepton colliders, electron-positron machines. The orange squares correspond to hadron complexes. And the lesson up until that point was, with increasing years and increasing energies, every time you built a new one of these fundamental accelerators, you discovered a new fundamental particle. And the aggregate of all of these processes was to assemble a picture which is very close to what we now call the standard model. There are obviously some missing ingredients here, but it included all of the fundamental force carriers except for gravity, and almost all of what we now know of as the fundamental particles. Okay. The other thing I just want to highlight about this situation is that you'll notice even though the lepton colliders are at much lower energies than the hadron colliders, they still have discovery potential. And that's because there's a trade-off inherent here. Whereas there's great energy achievable in colliding hadrons, they're composite particles, so you blow them apart and it's quite messy to reconstruct what happened. Whereas, although you can't get those high energies with the electron-positron machines, you can do so with greater precision, and so that has its advantages. And both of them are really drivers of discovery. Okay. So what did the actual landscape look like in 1984 as they were trying to figure out what to do next? So after surveying the successes of understanding the weak interactions and the strong interactions, which came about in the 1970s and 80s, they really were facing a series of questions like, what is the origin of mass? What kind of unification may exist beyond the standard model? What is the origin of flavor? And is there a deeper reason for gauge symmetry? And on the basis of these questions, the nature of these questions, and the way that they thought they could gain access to them, the conclusion was that the best way to go about addressing these questions was to proceed with the construction of the Large Hadron Collider. So, of course, that turned out to be the story. Before I briefly summarize how that story turned out, I want to focus just a little bit more on this first question, what is the origin of mass, especially for those of you who don't necessarily think about it in a particle physics context every day. So in the 1980s, why was the origin of mass an interesting puzzle? Well, to give you a very simplified version of the story, we know, at the time, we knew the force carriers of electromagnetism and the weak interactions, the photon, the W and Z bosons. Now, they're very different looking particles, right? If you look at them, the photon is massless, it mediates a long-range force. The W and Z particles are very heavy, they mediate a very short-range, weak interaction. So they look very, very different masses. But nonetheless, something surprising happens. If you imagine making some linear combinations of those particles, right, some particular linear combinations, you observe that they couple to the ordinary particles, the other fundamental particles in nature, in essentially the same way. So in other words, the fact that these linear combinations couple in the same way is an indication of some symmetry that unifies these interactions, even though they're very, very different looking types of particles. So this was the idea of electric unification. The electromagnetism and the weak force were actually the example of something that actually had some unity underneath it. So symmetry is great, right? If you take it to a theoretical physicist, if you take it to a high energy physicist, you say, I've got a symmetry. They'll say, great, symmetry is constraining. Let me go give you a prediction for the phenomenon that you should see. So if you imagine some hypothetical, maybe it's some AI-based high energy physicist, and you came to them and you said, I have the symmetry among the interactions of these gauge bosons. Can you tell me about the spectrum of my theory? Your AI agent without access to the real world would say, oh, I have a fantastic prediction for you. All of the other particles in your theory should be exactly massless, because the symmetry that you've seen is so constraining, I cannot write down masses for any of the other particles, so they must be massless. So this is your AI LLM prediction, is that the spectrum of all the particles in the universe, everyone is exactly massless. Of course, then you take it to a practical experimentalist who goes out and measures the spectrum of the particles, and they come back and they say, actually, not only are they not all massless, they have a dramatic, 5 orders of magnitude, more than 5 orders of magnitude range in the mass of the massive particles, some massless particles. There's also some other peculiar features, like there's a sort of repetitive structure in some of the masses. This is what the CERN-ECFA workshop meant by the question puzzle flavor, which also is somewhat mysterious, but crucially, these things have non-zero masses. So now there's a tension, right? There's a tension between this observation of a beautiful symmetry, which is clearly manifest in the interactions, and the vast spectrum of particles, which is dramatically at variance with that symmetry. So, of course, famously, there's a resolution to this. The resolution is the Higgs mechanism. So the idea is that there is a new field, the Higgs, which diffuses everywhere in space and time. It has a potential in the space of the field. So as you change the values of the field everywhere in space-time, the energy associated with it changes. So that's what this potential landscape means. And just by hypothesis, it has this peculiar structure. Since I'm from Santa Barbara, I like to call this the wine bottle potential. It looks like a punt in a bottle of wine, where at the origin of field space, where the value of the field is 0 everywhere in space and time, is actually unstable. And so energetically, what this field wants to do everywhere in space-time is roll off of the origin somewhere to the minimum, or the bottom of the wine bottle, where it takes on a non-zero value. So now everywhere in space and time, it takes on a non-zero value. And heuristically, all the things that would interact with this field, once it takes on this non-zero value everywhere in space and time, depending on how strongly they interact with the field, they acquire a mass. The more strongly they interact, the larger their mass. Okay, so this is the Higgs mechanism, and it allows us to reconcile this tension between the interactions, the symmetry of the interactions, which is a true symmetry of the theory, and the non-zero masses, which are not a property of the theory itself, but rather a property of its vacuum. Okay. Of course, famously, there was one more prediction, which is why Peter Higgs, among all the people who discussed this, won the Nobel Prize for it, which is that there's also a fluctuating degree of freedom around the minimum, which corresponds to a single scalar bosonic degree of freedom, which is the Higgs boson. So, thereafter followed from the 1960s onwards, right, a 50-year quest to discover this particle that would reconcile this tension between the interactions and the masses. And that, of course, was a primary goal of the Large Hadron Collider, which was triumphantly successful in 2012. And this is, the magnitude of that discovery, of course, was well captured by Dennis Overby in calling it the elusive particle seen as key to the universe. And I should say, I was again in New Jersey in the time when this happened, and this remains the greatest sort of period in my scientific existence was to be around in the air at the time when we discovered this new incredible fact about nature, the Higgs. Okay, so this was like the origin of the question: what is the origin of mass? The hypothesis for what explained it, and then the experimental verification of the thing itself happening at the LHC. So the motivation in 1984 led to an extraordinary discovery, and I think this picture, of physical argument to experimental test to discovery is a great validation of that idea. All right, so now we can play forward from 2012 to 2026, and we can ask where we are. The European community in particular has gathered again, actually, starting in 2025, but with the final judgment due now in 2026, to ask the same question that they asked in 1984. The LHC will run until the 2040s, but that means that now is the time to decide whatever facility actually should succeed the LHC. And of course, this question is not just being asked in Europe, it's also being asked in the United States. And as we'll see as the talk goes on, we're in the position where there's a divergence in the visions. I think that these two communities are very compatible visions, but there are two paths that the communities are choosing to follow. But okay, so what is the landscape, as of now, repeating this process now in 2026? So we played forward since 1984. We discovered more ingredients of the fundamental theory of nature, including the Higgs, but also the top quark and other neutrino degrees of freedom. And so now really we've arrived at what we now call the standard model, which includes 3 of the 4 fundamental forces. As far as we know it, all of the known particles, and of course the thing that is responsible for giving everything mass. So now the question is, what are the questions, given that this is where we are, what are the governing questions that motivate the future? And just something I want to mention before we do that is, we've been asking these questions and building these machines in service of this question about the fundamental structure of nature. But one of the reasons I think this is such a good idea, even if you don't care about those questions yourself, is that grappling with nature at the fundamental level, is a challenge of scientific ingenuity, which happens to give off lots of other discoveries and practical applications. And so the pursuit of these fundamental facts about nature has also given us lots of things that matter in the real world as well. Okay, so 2026, where do we go from here? Let's now play forward the scientific vision. So the first thing to do is ask, where are we in terms of those questions from 1984? So we had one, what is the origin of mass, right? We had to discover the Higgs. The remaining questions are open. So we've discovered a lot of things that are not the paths that nature has chosen. And that's not to say that theorists and experimentalists have been not working sufficiently hard. It's just that these are generational questions. And we are fortunate if we can make progress on any one of them in our lifetimes. So these questions are still with us, but we've also added more questions. Okay. So I only have an hour, so I'm not going to give you the full list of questions, but maybe two of the most salient ones that we added since 1984. One is, we had abundant evidence for the existence of dark matter, most of the matter in the universe, which is not part of that standard model table. So its nature is maybe one of the most driving questions animating particle physics. And then also we discovered that neutrinos have mass, which is not compatible with the standard model and its symmetries, even with the Higgs mechanism as we write it down. And so the details of actually what imbues the neutrinos with mass is also a pressing question that remains today. On top of that, although we've answered the question, what is the origin of mass? It's the Higgs. This is one of those funny questions where even when you answer the question, it then gives you more questions. It's a little bit like my 6-year-old, right? He has a question for me, I give him an answer, and then boy, do I have a lot more questions. So what do I mean by, we discovered the Higgs, why are there more questions? Well, this was put so perfectly by Frank Close in his biography of Peter Higgs that all I can do is just quote Frank Close to you. And so what he said is the more ambitious goal is to identify and understand the nature of electric symmetry breaking, the asymmetry that is key to the material universe. The Higgs boson is but its herald. So what does that mean? Well, to give that some substance, I'll give you an analogy for condensed matter physics. But before I give that some substance, I just want to now turn to, if these are the questions we have. So we have some questions that have resided since 1984. We have the new questions posed by discovery of the Higgs. And we have the additional new questions about elusive particles, dark matter, and neutrinos. And so the question is, what are the machines of discovery that we might aspire to build that would go ahead and allow us to make further progress? So there are lots of things that have been on the table, but what I want to do is just summarize a few of them that have come up in these processes in the United States and in Europe. So crucially, in the United States, sort of 2 years ago, we came to the end of our decadal survey process. This is something that started with a community study known as SNOWMASS. It went on to a federal advisory panel, and then also got this input from the national academies that I started the talk with. And in parallel, of course, there's been this process in Europe, which is underway. I've been very deeply involved in both of these processes. Thankfully, I'm also now going on sabbatical from all of this stuff. But we know what the answer is to this process, although it hasn't been officially named. But the process has been underway since last year. So what are the machines for discovery that have been discussed in this framework? So just to give you a sense of scale, this is, as a circle, the LHC, which is a 27-kilometer ring. And what it's doing now is colliding protons together, energies that are 14,000 times the rest mass of the proton. Something to keep in mind, I put some small print underneath here, is that when you smash protons together, you don't get to convert all of their energy into new things. Most of what you do when you smash protons together is you blow them apart. And you only get a fraction, because they're composite objects, you only get a fraction of that energy to make new stuff. And so the typical energy scales that we actually probe in these collisions are lower by about an order of magnitude. Okay. Now, the machines for discovery that are being proposed to succeed the LHC, so some of them, these ones in yellow, are electron-positron machines. The idea is, in some sense, to reproduce the successes of the LEP collider that came before the LHC. And the goal of those is really to study the Higgs boson as precisely as possible. Now, why that's a good idea, we'll get to in a second. But that's the idea for those machines. And you'll notice one of these circular machines is a dramatically larger tunnel. This tunnel, in fact, so this is what's known as FCCEE. FCC stands for Future Circular Collider. They're going to have to change their name, of course, if they actually build it. But this is the name it gets for now. And the reason it's in such a larger tunnel, so the good news, the reason why you want to collide electrons and positrons together is you get to convert all of their energy into new stuff. So you don't pay that price of blowing them apart because they're elementary. And also because they're not charged under the strong nuclear force, the final state is very clean. So it's easy to see what you've actually made. The downside is, as we know, when you accelerate a charged particle, right, you emit synchrotron radiation. And the amount of the power that's lost to synchrotron radiation goes like 1 over 4 powers of the mass of the particle. So that's not a problem when we're accelerating protons together in this 27-kilometer ring. But if you want to go to the energies that we need to study the Higgs boson with electrons and positrons, and you want to do it in a ring, you need to make the ring bigger because the electron is so much lighter in order not to lose a prohibitive amount of energy to synchrotron radiation. So that's why what's being discussed for this path forward would be something like a 100-kilometer ring.
But if the linear collider is smaller and goes to higher energies, why would you build the ring?
Good. So absolutely. So the other thing you could do, of course, is instead of paying the price for synchrotron radiation, you could accelerate electrons and positrons in a ring, in a line, and smash them into each other. There's sort of two reasons why you would pick the FCC over a linear accelerator. But absolutely, a linear electron-positron machine was one of the other things that's been in the discussion. There's two reasons you would pick the larger ring over the line. One is just luminosity. So one thing we need is we don't just need clean collisions with Higgs bosons, we need a lot of them to do good statistics. And the problem with linear colliders, it's a single-shot device, right? Every time you accelerate them up, you don't get to recycle the bunches. Whereas if you have a circular machine, you recycle the bunches till they're exhausted. So circular machines give you a luminosity or statistics advantage. The other reason is there's a great template historically for what happened leading up to the LHC. The first thing that was done was dig a 27-kilometer tunnel, which is quite expensive, and to line it with incredibly fancy magnets to collide electrons and positrons for the LEP machine. And then having already built the infrastructure, it was less of an ask to fill it with higher field magnets to build the LHC. And so the idea behind this FCC program is to benefit from that same logic. First, you dig this giant tunnel and you put a relatively inexpensive accelerator in it to operate at low energies for electrons and positrons. And then later, when your budget has recovered at CERN, you've developed magnets of sufficiently high field, you put in high field magnets and you collide protons together at much higher energies, 85 to 100 tera electron volts, so nearly an order of magnitude higher than the LHC. So that would be the second reason, is that there's an upgrade path to future energies that would come from the ring. But there's a third option that you see here that I've drawn in cyan, which is actually on a smaller footprint than even the LHC, which is the possibility of colliding muons. And so this is, you always know you're looking at a muon collider when you see a pair of rings. I'll explain why that is a little bit later. But the thing that you notice that's interesting about this is, in a much smaller ring, the idea is if you can collide muons together with energies of 10 tera electron volts, you're actually probing, because muons are themselves elementary, you get to use all of their energy to make new things. So you're actually able to probe energies that are much higher than effectively LHC is probing. And indeed, the energies that you're probing are actually competitive with the energies you would be probing, the genuine energies you'd be probing by smashing protons together at 85 tera electron volts. But you're able to do it in a much smaller ring because crucially the muon is much heavier than the electron. So you don't have to build a giant ring in order to survive the synchrotron losses. You can do it in a much smaller ring. And in fact, as I'll discuss, the smaller ring is the better for having to do with the fact that the muon is an unstable particle. Okay. So these are sort of the options, the machines for discovery that have been on the table. Before telling you about how they can make progress in these fundamental questions, I want to just give you the basic idea about how each one of them gets at these fundamental questions in a different way. So if you're trying to discover new particles, you can ask, as a function of energy in which you're colliding your particles and the rate for making some sort of final state that you're interested in. Most of the time, what's happening is you're producing some standard model process, which I've shown in blue, something that you know, which maybe is a process whose rate falls as a function of energy. But if there's a new fundamental particle out there at some scale, if you can now collide things together at sufficiently high energy, you'll now hit a resonance for whatever final state you're in, where you're now producing real versions of that new particle at some high energy. Okay. So at the end of the day, if you can probe all of these energies, your rate for some final state will look like a falling standard model process, and then eventually at sufficiently high energies, a new bump that is well in excess of what you expected. And that is discovery of a new particle. Okay, so that's where you're doing alchemy, you're sitting on the resonance of a new state, you're smashing things together and making something new. But I want to emphasize, so here I should say, by the way, the role of new is played by whatever thing is being exchanged. But I want to emphasize that to discover something, you don't just have to get to these high energies, right? You'll notice that even before you hit the energy scale where you're making a physical version of the new particle, there's a departure from your standard model prediction because you're starting to tap into modifications due to the new physics. And from a particle physicist's view, what's going on is if you zoomed out here, you wouldn't see a particle being exchanged, but you would see new interactions between the particles you already know about. And those new interactions would give rise to deviations from the standard model itself. And this is important to emphasize because this means that there's really two different ways of getting a discovery. One of them is actually to build low energy but incredibly precise machines. So the sense in which electron-positron machines are machines for discovery is they're not necessarily going to sit at energies where they're making new physical particles. Instead, what they're going to do is make incredibly precise measurements of standard model processes and be sensitive to these very small deviations from the standard model prediction. So that's a sense in which they're still a machine for discovery. On the opposite end, of course, there's proton-proton machines. And as I've described, if I have a proton-proton collider that's operating, say, at this energy, typically the things that you'll use to discover it are at lower energies, right? Because you don't get all the energy in the protons to make something new. You have to sample from fractions of energy contained in the constituents of the proton. All right, so you build them at energies higher than the scale that you want to grow. And the reason muon colliders are interesting is that they actually give us a totally new way of going about this question. They sit in between these two poles. So as I mentioned, in muon collider, you get all of the energy in the collider to make new things with some rate. So you can discover particles up to the energy that you operate the collider. But also, muons, very high energy muons, have a very interesting property that they actually are surrounded by a cloud of virtual particles. And the collisions of those virtual particles carry less energy, but also give you interesting statistics. So you can discover new particles not just at the collision energy of the collider, but also at much lower energies by using these sort of auxiliary quantum mechanical processes. So just to give it to you in pictures, you should not think of high energy muons as being a fundamental particle flying through space. You should think of them as being surrounded by a cloud of other standard model stuff. And occasionally that cloud can interact with each other. And that can also give you, although with lower energy, better statistics than the annihilation of the muons themselves. And so this is a sense in which a muon collider kind of blurs this dichotomy between high energy, but blowing up protons, and low energy precision of electrons and positrons. Okay. So this is starting to give you a sense of why muons are an interesting idea. Okay, so now we've talked about what are the questions we're facing. We've talked about what are some of the machines that are being proposed to address these questions. And so now necessarily the question you have is, how do these machines possibly make progress? How do they really pose a new way of getting at these questions that are left in the wake of the LHC? Okay. So let's now turn to that. So the first thing is, let's come back to this question of the origin of the Higgs mass. And I told you Frank Close is encouraging us not to think of the Higgs discovery as the end, but rather the beginning of our understanding of the nature of electric symmetry breaking itself. And to explain what that means, I just want to give you a condensed matter analogy, right? So, more than a century ago, with the discovery of superconductivity, the first effective description of superconductivity, theoretically speaking, was what we call the Ginzburg-Landau effective theory, which was a description of the free energy of the superconductor close to a superconducting phase transition. And so this was an effective description in terms of an order parameter, and its free energy had, what as a particle physicist we would call looked like a potential of the exact same shape as the Higgs in the Standard Model, right? Also a Wien bottle potential, and this is what described the superconducting phase transition. Okay, so this is a perfectly good description of the phenomena of superconductivity at the phase transition, but it turned out this was far from the end of the story, right? This was not a microscopic description of what was going on, but an effective phenomenological description. Of course, ultimately, there came about the BCS theory of superconductivity, where we discovered the actual phenomena that underlay superconductivity, the formation of Cooper pairs. And this was now a microscopic description. But having the microscopic description, we could then go ahead and derive the parameters of this effective theory. The parameters, of course, in the effective theory themselves were simply things you had to measure. But now we had a microscopic theory from which we could predict them. And the situation is identical for the Higgs boson in the Standard Model. Right? The potential that we put in the Standard Model to explain electric symmetry breaking is simply a Ginzburg-Landau effective theory. We cannot predict its parameters from first principles. We simply fit them to data. Okay? But what we are in search of then is a deeper theory, a microscopic theory, of which this is the effective description. So hopefully from that perspective, it's clear why Frank Close says that we discovered the Higgs boson, that's just the beginning. That's like discovering superconductivity and the Ginzburg-Landau theory. And now our aspiration should be to figure out what is the BCS theory of electric symmetry breaking. I want to emphasize, actually, even that is an overstatement of the current state of affairs. Okay? We say in the Standard Model with the Higgs mechanism, we have this Wien bottle potential. This is a beautiful explanation of what we've seen. And it sounds like we know that this is the picture. Right? Okay. But funnily enough, we actually have absolutely no idea that this is what's happening. Okay. So to give you a sense of how little of an idea we have that this is what's happening, given our state of knowledge at the LHC, I want to draw a picture where imagine taking a slice across this Wien bottle potential that just follows the curve from the origin on out to the edge. Okay? And then I want to draw error bars that give you a sense of our current knowledge. So here's a slice from the origin to the edge. And this shaded region is giving you a sense, as you change the value of the Higgs, our knowledge of the shape of the potential. Okay, these error bars include basically all of the possibilities consistent with current data. And you can see, you can fit inside these error bars dramatically different shapes, right? They look absolutely nothing like this wine-level potential. So we don't even know that this is what's happening. That is how dramatic our ignorance of electric symmetry breaking is at the moment. I should say for the graduate students in the audience, this seems like a nice way of parameterizing our ignorance. It's very visual. Hopefully you all have a visceral sense of what's going on. This wasn't something that people did for a long time. This came from a suggestion by a graduate student visiting UCSB 3 years ago. And now it's being used in the documents that are sent to European ministers to make the case for future colliders. So you as graduate students can also influence European ministers. That's a sufficiently clever idea. You should never underestimate the value of the visual representation of information. Okay, so the good news is actually we will make considerable progress on this during the remainder of the LHC. So I don't want you to get the impression from my talk that the LHC is no longer interesting. We have a lot of great physics to do there. And one of the things we'll do is to dramatically sharpen this picture. So these are approximately the error bars that we expect to have on the shape of the potential by the end of the Large Hadron Collider era in the 2040s. But there's still a lot of sort of funny things that you can fit in this envelope. But to give you a sense of the stakes, what these future colliders that are being considered could do, whether it's a linear collider, as we discussed, or the proton-proton version of this 85 TeV collider or a muon collider, as you can see, the precision that we get in the measurement of the Higgs interactions, and therefore the inferred value of the Higgs potential, really has the potential to dramatically draw this picture into focus. So really, this is where we will learn if, in fact, this is how electric symmetry is broken. And I want to emphasize, this is interesting, even if all of the data we get is consistent with the standard model, then we learn that, in fact, this is what's happening. Of course, if we see any deviation from the standard model prediction, then we know that our picture of the universe is dramatically incomplete, and who knows what happens after that. Another point I just want to emphasize in passing is the other thing, if you want to understand electric symmetry breaking, of course, we care about the shape of the Higgs potential. We also care about how the Higgs gives mass to all the other particles. And as I mentioned, that's tied up in how strongly those particles couple to the Higgs. So then you could say, great, let's measure the strength of those couplings and ask if they agree with the prediction that we have in the standard model. I don't expect you to read the soup of bars. All they're doing is showing you, for any given particle in the standard model, our knowledge of the strength of the coupling of the Higgs to that particle relative to the standard model prediction. The gray bars are showing you the percentage precision we get to the LHC. And I want to emphasize, you'll see the axes are sort of in percent. And that itself is an extraordinary triumph of the LHC. When the LHC was designed, they actually thought even the discovery of the Higgs itself was impossible. And now we're talking about using the LHC to measure Higgs couplings to the few percent level, which is just a statement about the triumph of experimentalists in this landscape. But the thing I want you to also pay attention to is the order of magnitude improvement that many of these proposed colliders give you. Some of them are sort of obvious. Some of these improvements are coming from these lepton colliders, which have very high precision measurements of the Higgs. But the other thing that I want to point you to is, I know the color scale is hard to read, but for example here, this bar, so almost at the per mil level, is telling you how well we would measure the Higgs coupling to Z bosons. And that bar is about the same for a muon collider and this giant circular E plus E minus machine. And what that is telling you is a real testament to the sense in which a muon collider blurs this dichotomy. You're going to very high energies in muon collider, but you also get extraordinary precision that's so good that it competes with a dedicated factory that was designed to discover the Higgs. Okay. So these questions, they're not just about what's the shape of a wine bottle potential, right? Like there's a more existential meaning to these questions. It sounds hyperbolic, but in a very real sense, measuring the properties of the Higgs and its potential are actually telling us something about the birth and the death of the universe that connects to fields, of course, that are outside of particle physics. So in terms of the birth of the universe, right, we have this idea that as you heat up the universe, as we know, finite temperature has a tendency of restoring symmetry. And so in the case of the Higgs, the idea is that as you heat the universe up, instead of having this zero temperature wine bottle potential, at very high temperatures, you have sort of a bowl, and the Higgs there wants to restore electric symmetry. Okay. And so then conversely, as you cool the universe, we go from the symmetric phase to the broken phase. Now, in the standard model, anytime you have a phase transition, of course, a very interesting question is what's the order of the transition, and what are the associated phenomena? If the potential is as the standard model predicts, then we know this is a second order phase transition, and there's a smooth crossover. But if there are modifications to the Higgs potential of the sort that we will become sensitive to, then it's very easy to switch from having a smooth second order phase transition to having a violent first-order phase transition, in which case the phase transition happens not by a smooth switching on of masses everywhere in the universe, but rather the nucleation of bubbles of the broken phase inside the ordinary phase, just like making gas bubbles in boiling water. And of course, then what happens is these bubbles expand, they propagate, they collide, and they create a new universe in the broken phase. But this is interesting for all sorts of reasons, right? Particularly astrophysical and cosmological ones, because among other things, the completion of such a phase transition would give us a spectrum of stochastic gravitational waves, which we can look for in future gravitational wave observatories. So there's a very tight connection between the measurements that we make about the shape of the Higgs potential and the sense in which electric symmetry was broken as the universe cooled down, and complementary measurements we can make in other systems. Just to give you a sense of how tightly we can narrow down in this question, again, I don't want you to pay too much attention to the soup. I have to unfortunately take the blame for making this plot for the European strategy update. This is just a statement of, with the precision that we measure the Higgs coupling to itself, so the Higgs potential, and the precision that we measure the Higgs coupling to the Z boson, you can ask, if I added a new particle that would change the Higgs potential, that would make this phase transition strongly first order in the early universe, that corresponds to all these dots. So this is sort of the region where we've added something new and the phase transition is first order. And that predicts deviations in the Higgs couplings. And then you can ask, depending on the colliders I build, how tightly can I constrain or discover these possibilities? And again, the lines are all the soup. But the punchline is, if you build a muon collider, this is now the space that remains unexplored by the measurements that you make. In other words, the vast majority of all of the parameter space where there could have been a first order phase transition and gravitational waves are things where we could also discover the ingredients responsible in our precision measurements of the Higgs. Okay. It's also tied not just to the birth of the universe, but the death of the universe. It turns out if you study the Higgs potential as a function of scale in the standard model, at some point, the potential actually turns over. We don't know what happens at very large values of the field, but quantum mechanically, that means there can be tunneling processes that take us from our very happy vacuum to some other place, and that would correspond to a spontaneous death of the universe. Right now, given what we know in the standard model of its parameters, we know we live in an area of metastability where the lifetime of the universe is dramatically longer than any time scale we should care about. But exactly where we live in this space depends sensitively on the shape of the Higgs potential, and again, is something that we stand to learn about. We said, so that's just the shape of the Higgs potential and what it tells us about the beginning and end of the universe. This question of what is the BCS theory of the Higgs? In other words, what's the microscopic theory that gives us the Higgs potential? Here, I just want to say, if the Higgs is like Cooper pairs, then it's a composite state, and we should be able to actually see evidence for its size. At the level of particle physics, seeing evidence for its size is to find new contact interactions, which show up in the couplings of the Higgs to other standard model particles. Where we'll be by the end of the LHC is we'll be able to probe whether the Higgs is composite at about the same level as we know that the pion is a composite degree of freedom of strong interactions. But to push beyond that into really qualitatively new grounds, to know if the Higgs is the most elementary scalar we've ever seen, we again need these future colliders, which will improve our knowledge of the Higgs as a composite object or an elementary object by an order of magnitude. The last thing I want to mention in terms of the BCS theory of the Higgs, if you'd only known about superconductivity and you didn't actually know about, say, electrons and phonons, as you tried to figure out the microscopic theory, you might go ahead and discover electrons and phonons as a consequence of this low energy description that we've had. And you can ask the same question for the standard model. Again, in the standard model, we can't predict the Higgs potential, but we can imagine that the standard model is a piece of a larger theory where we can calculate the Higgs potential parameters in terms of other things. And then we could say, okay, what are the masses of the new particles in this extension of the theory? And can we now go ahead, given the properties of the Higgs that we see, can we go ahead and discover them? And this is really where the high energy colliders, like the high energy proton machine and the muon collider, come in handy, because in calculable models where you can actually predict the mass of new particles given the properties of the Higgs, you see that the mass scale where they should show up is beyond the reach of the LHC, but for the most part within the reach of the colliders that we propose to build. I want to briefly tick the other boxes on our list very quickly, and then get to the question of what's really at stake in terms of realizing this vision. There's this question of what kind of unification may exist beyond the standard model. This is the amazing statement that if you take the coupling strength of the standard model forces down where we measure them at the weak scale, you can then extrapolate them to higher energies using quantum mechanics. And you see something very peculiar happens. They almost all come together at one point at many orders of magnitude and energy above the scales that we operate at. But there's two failings in the standard model. So this is a suggestion that all of the forces should unify. They come very close to doing it. But there's two problems in the standard model. One problem is they don't quite cross in the same place, so they kind of miss each other. And the other is that actually, if they did cross around here and they all unified into one place, you would predict that the proton should decay with a lifetime that we have not yet seen. So it's ruled out, the proton is more stable than this naive picture would suggest. So then you could ask, what would it take to change the story to have the precision of the crossing be greater and to have the scale of the crossing occur at higher energies, which would make the proton more stable? And unsurprisingly, the way to change how these couplings evolve as a function of scale is to add new particles down at the lowest possible energies to give you the longest possible time to bend the couplings as you go to shorter distances. And so this is just a statement that if you think that the suggestion of unification is a good hint to microscopic physics, the place you'd expect to see new particles is actually down at the scales that we hope to probe. So even though unification of all the forces in the standard model is at abstractly high energies, the place where you might look for evidence of it is potentially within reach. The origin of flavor, as I mentioned, we have in the standard model these patterns of fermion masses that seem to repeat themselves. So this is called the puzzle of flavor. In our pattern finding brains, we think it's a sign of some structure. We would like to figure out what that structure is. All I want to say about these future colliders is even though they're meant to be machines of discovery, they also give us great access to these questions. For the electron-positron colliders, it's actually because they will in some sense be the best machines for studying the properties of standard model flavor interactions that we've yet made. In the case of a muon collider, there's a very simple idea that a muon is part of what we call the second generation of standard model particles, right? It's a cousin of the electron. And it won't surprise you that if you take particles that are higher up in the flavor structure of the standard model and you smash them together, that's sort of the best way that you could actually get access to whether there's deeper structure behind standard model flavor. So there's great potential here as well. There was this question from 1984, is there a deeper reason for gauge symmetry? And if you think about measuring even just the standard model interactions as a function of energy, there's extraordinary sort of emergent phenomena that is revealed to us having to do with the gauge interactions as we go to higher and higher energies. So if you can imagine increasing the energies at which you're probing the electroweak theory, a variety of things happen as you go up in scale. The first is you go up and you probe the scale of electroweak symmetry breaking. I've already talked about that exhaustively. There's actually even a question of once you go above the scale of the Higgs and begin to probe its potential, this question of whether the shape is the one that we actually expect and whether electroweak symmetry is actually restored as a symmetry of the theory once you add the Higgs or if there are additional ingredients required. But other amazing things happen as you continue to go up in energies above about 3 or 10 tera electron volts. One of them is actually you start to see that electroweak symmetry is restored in the collisions of your particles. You get to see also extraordinary things like what we call Goldstone equivalence, that the scattering of longitudinal polarizations of the weak bosons is equivalent to the scattering of Goldstone bosons. And that's something we could see experimentally at a few tera electron volts. And as you go to even higher energies, something truly remarkable happens. The W and Z bosons become effectively massless, and they really start to act like electromagnetic radiation. And so in some sense, you can actually start to see classical weak radiation as you probe the theory at sufficiently high energies. And the reason I want to emphasize this is even if there's no new particles within axis of our future colliders, there is fundamental phenomenon in the standard model itself that we have not seen experimentally that we stand to understand as we build these machines and operate them at higher energies. Okay. The nature of dark matter and neutrinos, so we'll tick the last two boxes. So as we know, most of the universe is not standard model stuff. It's dark matter, at least in the matter density. I have nothing useful to say today about dark energy. Of course, we have a plethora of candidates for what dark matter could be. So of course, I'm sure Josh and Neil are happy to tell you about all of the candidates that live in the space. But there is still, at least to me, when I get out of bed in the morning, what I tell myself is probably dark matter is an old but beautiful story that if there's new particles in the universe whose masses are around the weak scale with weak scale interactions, that as the universe cooled, they gradually fall out of equilibrium and they give us the amount of dark matter that's approximately what we see today. So it's a beautiful story, the WIMP miracle. We've had it for a very long time. The way that we currently pursue, for the most part, experimental evidence for the WIMP miracle is we say, well, if this dark matter is ever in the universe and it has weak interactions, then we should wait in very carefully instrumented detectors for it to scatter off of our detectors. So to see scattering processes where the dark matter scatters off the standard model. So of course we do that in a number of beautiful dark matter direct detection experiments. But there's a bit of a problem if you're a true believer in the WIMP miracle, which is that in some sense, the simplest weakly interacting dark matter candidate, the absolute simplest thing you could add to the theory that would bear fruit to this story for dark matter, you can go ahead and calculate the cross-section it gives you for scattering these detectors. And unfortunately, it's an incredibly small cross-section, in part due to some accidental cancellations in nature. And it turns out, not only is it beyond the reach of current experiments, it actually lies in the space of cross-sections that's dominated by neutrino interactions. And so it's an incredibly hard signal to pull out. Now, that doesn't mean it's hopeless in these direct detection experiments, but it means it will be a very long journey to discover dark matter if this is what it's doing in the simplest incarnation. And what's remarkable in particular about muon colliders is now we can produce this dark matter in a different way. We can annihilate the muons and actually use that to create the dark matter. This is something we also look for at the LHC, but the LHC is a very messy environment, whereas a muon collider has both energy and a clean background that we'd actually use to pick out the very subtle signatures of dark matter in this situation. And so it is a remarkable fact, and in fact, one of the key, I think, arguments for muon collider over other colliders, that the colliders we propose to build, smashing muons together, are perfectly positioned to discover this dark matter candidate if it's there. So this would give us a complementary test of this hypothesis for dark matter. And finally, just to touch on the nature of the neutrino sector, we normally don't think about probing neutrinos at high energy colliders, but there are many senses in which a muon collider in particular is a great source of neutrinos. Among other things, it's because the muons themselves are decaying into neutrinos, and so we can use that as an interesting neutrino source. Just to convince you that this is interesting, you can ask, if you operated a muon collider, and ask what is the spectrum of neutrinos that you would produce, how many of them as a function of the energy. The muon colliders that we propose to operate are giving us orders of magnitude more neutrinos at very interesting energies where we don't have otherwise well-controlled sources. So this is sort of a beautiful way to understand the properties of neutrinos by using the sort of parasitic production of neutrinos in the operation of the muon collider. There are lots of other places where we learn about neutrinos from the construction and operation of a muon collider. And so again, for me, what makes this so beautiful is that right now in particle physics, we are in a bit of a period of divergence where, for example, the experimentalists studying neutrinos and the experimentalists studying the Higgs boson seem to be speaking different languages. But this is a context actually where the physics interests of these communities are really commonly developed. Okay, so in this lightning tour of the questions that we face in 2026, hopefully I've at least partially convinced you that the machines we propose to build, and in particular muon collider, is really the right machine given the nature of the questions that we face. And that there's a qualitative sense in which we're not just on a fishing expedition. The sort of interesting experimental targets that are posed by these questions are within the reach of the machine that we propose to build. So the last question you have in the last 5 minutes, from when do I get to go home, is what will this actually take, right? If a muon collider is such a great way of probing physics in the standard model and beyond, why don't we already have one? So to give you a sense of that, in fact, on all these colliders that are under consideration, I want to show you a timeline. And this also plays into the reason why in the United States, we've decided to focus on construction of the muon collider. So this is my version of a timeline that starts in 2025 and runs past 2070. On the top is the timeline of this future circular collider complex. So building this electron-positron machine and then a proton-proton machine at CERN. On the bottom is the muon collider timeline, assuming that funding exists to stay on the technically limited timeline. So in the case of the FCC, the primary constraint is the Large Hadron Collider is running in the 2040s. And so although it's possible to start constructing this larger tunnel and to start building this electron-positron machine, in some sense, the timeline for actually starting collisions has to necessarily begin after the LHC has been decommissioned. And then once you've done that, there's a long program of measuring the Higgs boson and other properties of the standard model of low energies. After you've done that, in the 2060s, you can start taking out the electron-positron machine and putting in the proton-proton machine, and you get collisions in about 2075. And you can see, of course, what the challenge is here. We stand to learn a lot from precision measurements of the Higgs and electron-positron machine, but to push the frontiers in energy, right, the first collisions that we make in that would start after a PhD who begins now has necessarily reached mandatory retirement age at CERN. Right? So there's a sense in which the access to the energy frontier questions in this timeline are beyond the lifetime of an experimental physicist starting now. And this is a bit like asking people to get on a spaceship to go outside the solar system and knowing that not they, but their children will arrive at the destination. It's an ambitious ask, but it's a difficult one.
It's a little bit different than die in space, far from
Yes, right, that too. So yeah, at least
an American job.
At least for terrestrial, okay. So in the muon collider, you'll notice, so the actual timeline for getting data, which is probing the same physics that's being probed out here in the future circular collider, is much closer. So it would be around the same time as the electron-positron machine at CERN. The reason it's not sooner is you'll notice there is a sort of 10 to 15 year period where instead of simply beginning construction, there's R&D and technology demonstration. So, and this is the obvious fact that needs to be emphasized, whereas we know how to build electron-positron and proton-proton machines, we just need to develop some of the necessary magnets. There are some important fundamental ingredients in building and operating a muon collider that we need to demonstrate before we can go ahead and do it. And so that is a sense in which this is a riskier proposition. So the physics case is arguably stronger. The fact that it can live in a small tunnel makes it cheaper, but there is a demonstration of technology that is required in order to make it feasible. We'll get into that in just 1 second, but you can see at least graphically why it is that I think, especially in the United States, the idea of this sort of machine is very compelling because it brings these sort of questions into the reach of people who are currently asking them in the field today. So what is the R&D that has to be demonstrated? This is if you take the sort of double ring of a muon collider and unfold it into all of its bits. A lot of these things are not so hard to do. We're pretty sure we know how to do them. But the thing that is a really interesting challenge is what's known as the cooling of the muons. So anytime you want to make a particle accelerator, right, you make the particles themselves, and then you have to cool them in phase space. So of course, we want them to be very energetic by the time we collide them, but we want them to have very little dispersion so that we know exactly the energies and directions in which they're headed. And for muons, that's hard, right? So for electrons and protons, that's easy because we have lots of ways of cooling them and because they're stable. Whereas in the case of a muon, it decays in microseconds in its rest frame. And so that means you don't have a lot of time to cool it down before you actually try to collide. Now, it's not hopeless because, of course, we're accelerating these muons up to very close to the speed of light. So the laboratory frame, they can live long enough to do something useful with them. But you still have to act very fast, and you can't use any of our existing methods to do it. So the best option we have right now is something called ionization cooling, where you basically pass them through a material with long radiation lengths, and you use that to bleed off the transverse components of their momentum. This is we know the physical principles, but the demonstration that this works at the scale necessary is something that remains to be done. But the thing I want to emphasize is while this was considered futuristic for many decades, at least in simulation now, we've demonstrated that we can do ionization cooling end to end in a way that is better than the goals that we need to build such a collider. So R&D and demonstration is necessary, but the physics targets themselves are within reach. The other point that I want to emphasize here, so this is an unfolding, this is actually what it looks like if you put it all together. And something else that's interesting and compelling about this for the United States is the ring that you would need to build a 10 TeV muon collider fits on the Fermilab campus. So this is a lesson that we learned the hard way many decades ago. If you want to build new accelerator facilities in the United States, the best bet is if you can do them in national laboratories that we already have. And it's the extraordinary fact that, in fact, the muon collider fits on the campus. Now, I promised I'd tell you why a muon collider has a double ring. You see it here, you see it here, and you see it here. And the answer is you've made the muons, you've cooled them down, then you need to accelerate them up to collision energies. And so to do that, it's advantageous to have a larger ring. But then once you've got them up to collision energies, you want to have a smaller ring because they're eventually going to decay. And so you want them to be able to have as many passes across each other as possible before they disappear. And so that's why once you've accelerated them up to speed, then you actually want to circulate them in a smaller ring. And that's the reason for this double ring structure. Okay. More broadly, for a long time, if you talk to people who've been in the collider physics game for a while, they're often dismissive of a muon collider because for many years, there were what were called the 12 miracles. Right? Miracles, of course, makes it things that you'd have to do be possible in order to build a muon collider. And miracles makes them sound impossible. But what we've discovered in the last few years is that these, in some of these are actually already solved, and some of them are simply challenges that we know how to solve, and all we need is the R&D to fully demonstrate them. So one example, as I mentioned, is the ionization cooling, where at least in simulation, we know it can be done. Others are the types of magnetic fields that are required. And in fact, in many cases, the magnets that would be needed here already exist elsewhere in physics and other disciplines. And so really, we've shifted from 12 miracles to 12 challenges. And the question is just, do we have the commitment to go ahead and demonstrate all of these to build the collider? Okay. So the convergence of all these factors, the idea of the physics questions we face, the muon collider and the way that it is uniquely suited to answer them, and its relevance on the timescales that matter for human beings, has now led to a remarkable series of events that have unfolded in the US over the last 4 years. So it started with the US sort of decadal survey process, the community survey process in particle physics, which made a recommendation to start research and development for muon collider, ending in demonstration and then potentially construction on the timeline I articulated. That recommendation then went to the federal panel that advises the DOE and the NSF. They built upon this recommendation to indeed advocate for the R&D program necessary to build a muon collider cited in the US. And then that's, of course, what brought us to today, which is this National Academies panel, which took all of this input, but also its own unique vision of the field, and arrived at an even stronger recommendation that the United States should build a muon collider in the US around the middle of the 21st century. So that's now answering the question, how did I get here? So here we are. Now, one thing you might be wondering, and I promise I'm almost done, is this all just pie in the sky, or am I just telling you some story heedless of the consequences, the challenges, and needless to say, the expense? But something I think those of us who are thinking about this now, advocating for this picture, I just want to emphasize that we're doing it with a great sense of realism, with a great conscious sense of the perils of getting it wrong. To sort of drive this home, well, I'm showing you this picture. So is anyone who is not with me at lunch today, does anyone know where this picture was taken?
Is that the superconducting super collider site?
That's right. This is Waxahachie, Texas. So if you drive south of Dallas for about 30 miles and you take the Waxahachie exit, you drive down a farm road for a few miles and you pull off on a gravel shoulder. You walk about 200 yards into this field and you'll see what, to all intents and purposes, is the graveyard of American particle physics. So this is about a 60 by 30 foot ellipsoidal depression. Okay, it doesn't look like much if you're standing up by the side of it, but you may recognize it from a very famous image of the superconducting supercollider. So this was actually the top of a magnet delivery shaft. So what you're seeing here is that ray of light up there. This was to be one of the main caverns in which they built detectors and through which magnets were being delivered. So of course, that's to say, we have this very complicated history of ambitious accelerator physics in the United States, where we aspired to answer many of these questions in the 1990s with the superconducting supercollider. And for various reasons, of course, that project was canceled. And it was canceled even when it was really on its way to construction and operation. And this has been a tragedy that, of course, has set back American particle physics in a very serious way. But thinking about it positively, right, it gave us a lot of lessons about the stakes. And so when we develop this picture and we advocate for a muon collider in the US, we're doing so very much conscious of the perils of getting it wrong. And this is one of the reasons, for example, the fact that a muon collider, among all the options, could be sited on an existing national laboratory campus is so important for us. So, of course, it's reasonable to ask, given that it is nonetheless very hard, and given that we have this perilous past, why am I advocating for this and not something simpler with better job security? I think when it comes to advocating for something that's very hard and challenging, there's no one better to inspire us than JFK. So if you'll forgive me for a second, everyone with me now. We set sail on this new sea because there's new knowledge to be gained across the frontiers of particle physics. Hopefully I've convinced you of that with the questions we now face after the discovery of the Higgs. So we choose to collide muons. We choose to collide muons in this decade, not because it is easy, but because it is hard, right? Because this goal will serve to organize and measure the best of our energies and skills, because that challenge is one we are willing to accept, one we are unwilling to postpone, and one that we intend to win. So thank you very much for giving me a chance to tell you the story today, and I'm happy to answer any questions you might have.
Questions? Okay, so after these kinds of talks, some of my grumpy colleagues, not me, but my grumpy colleagues, will say, this is a lot of money to change some error bars, right? And this space analogy actually, I think, really doesn't do any service, right? Because, yes, we went to the moon because it was hard, but also went to the moon because we wanted to beat the Russians there. And you could see obvious technological applications for spaceflight that we've seen today, right? My life has very much changed because of spaceflight, right? How has my life changed because of the top quark or the Higgs boson, right? Like, I mean, if you're talking billions of dollars for this, like, why is this what the science budget should go for?
So a couple of things. So first, I just want to thank you for asking the hard questions, because I think we don't do any of ourselves any favors by dancing around, right? We have to tackle them head on, and we have to convince ourselves that this, among many options, is the right thing to do. So I just want to express my appreciation for you to ask that question. And you can even ask me that question in a grumpier way if you like. I totally understand. But just a couple of things. So one is, it's an interesting fact that the cost of these machines, so it used to be historically, and certainly during the SSC era, that the cost of these experiments was dramatically out of scale for any other experiments in science. Okay. The cost of a muon collider is within the same ballpark as the cost of JWST. So it's simply the case that frontier science across many domains of physics has grown to the point where this is not alone among all possible experimental questions that can be asked, but is in fact commensurate with the types of experimental questions that are asked in other fields. And I think hopefully we can agree that the thing to do in this situation is to recognize, honest intellectual endeavor among these fields, and to work together to recognize that projects of this scope in different fields can and should be constructed, and they should not be seen as a zero-sum game where we get to build the next shitty WST with no future colliders or vice versa. It's just that the scope of the actual cost is not dramatically out of scale compared to other experiments. And that's just, I think, important to emphasize. And indeed, as a fraction of GDP, the fraction of GDP required for muon collider is dramatically less than the LHC or the SSC that the collider before. So fractionally, this is, I'm not going to say it's cheap, but it's not that expensive. There's a couple of other things I think that are worth highlighting. So there are obvious technological developments that would come out of muon collider. One of them is, of course, not just the high field magnets, but also the fast ramping magnets that are required to get the muons up to speed once you cool them. That's a really interesting technological challenge. As we know, the high field magnets that came out of collider development have also been a great boon for all the sciences. So there's some clear deliverables just in terms of the direct technology. The other thing I think that's worth emphasizing is that when you grapple with the hardest questions in nature, right, that is in some sense the greatest, seed of innovation. And I think that's demonstrated by talking about all the things that have come out of the previous development of colliders. So no, this is not something where I can point to you and say we're going to do X, Y, and Z, but rather it is the informed expectation that by pursuing this path along with other paths, there are many things that are unforeseeable that can come out. So I think that's also worth emphasizing. The final thing that I want to emphasize is the sense in which, and I hope I've articulated it, and this is why I think to me a muon collider is worth arguing for beyond the other colliders that are also being discussed, is that it does represent a convergent path for the questions across the vast expanse of particle physics. Right? These days, particle physicists, depending on who you ask, are interested in dark matter and neutrinos, the Higgs mass, the Higgs boson, all these other questions. And this is the one place where I actually see these questions coming back together. So as a concentration of resources and capital, it's in some sense the best way, rather than splitting this money up into 10 different ways to ask fractional versions of the questions. It's a convergent pathway. The final thing I want to mention, it's a little hard to completely convey the quantitative nature of this in this talk, but these physics targets that I've given you, they're not just improving error bars. I think there's a real criticism of this electron-positron collider that you are just tightening error bars, because that's really what you're doing. You're getting a factor of few improvement on Higgs couplings. Okay. But at a 10 TeV muon collider, there are quantitative thresholds of phenomena that we cross. Okay. So one of them, again, is like classical electroweak radiation or Goldstone equivalence, this experimental phenomenon. That's even if we just have the standard model and nothing else. Like if you told me today, just the standard model, there's still new phenomenon that we discover at these energies, experimentally observed, which I think, in any other field of science, right, that is the gold standard. It's just the funny thing in particle physics, we've also set ourselves the standard of discovering new stuff. Okay, but if we set that aside for a second, we're meeting that standard with these machines. It's not just improvement of error bars. And so I think that's really so important. Of course, then also on top of that, if you're in the quest for discovery, there are these very sharp targets which we also can reach. So the very sharp mass and coupling target of minimal electric dark matter, we know we get to. Now, nature doesn't have to have given us that, but it's not just some theory I made up for you. It is in some sense the simplest and best explanation for what dark matter is, and we know we can get there. So it's also with care that we've measured these targets and we've seen what it takes, what energy is required to get there. And then it just turns out to be fortunate for us that that fits on the Fermilab campus. But I appreciate the hard question.
So the date of 2075 as the target is very scary, and not because that it just takes long. Things can take long, that's normal. But plans exist so that there is something that can go wrong. And how realistic is 2075? Like, are there a lot of things that can go wrong so that it will be like
for the proton-proton machine, the 85 TeV. So and this is I think where there are these diverging paths of European and American plans. So the U.S. exploration is this path of R&D for muon collider. That if in 10 years of R&D we can demonstrate ionization cooling and the other thresholds are achievable, then we can proceed with construction and operation of the collider in the 2040s, 2050s. Okay. But it is possible after 10 years of R&D that we decide that we cannot build a muon collider to the specifications we require for the physics targets. And if we can't, then that is an end point of that quest. Whereas where Europe has converged, because they have CERN, and there is this primary interest of course, ensuring the survival of CERN as an experimental facility, there a more conservative choice is made, technologically speaking, right? So that's why in Europe, the decision is being made to proceed with this 85-kilometer tunnel, which will first do Higgs physics with electrons and positrons, and then in the 2070s be upgraded with 16 Tesla magnets to do proton-proton collisions at 85 teraelectron volts. So the timeline is much longer, but in some sense, the technology is more guaranteed. Like we do have to be able to construct at scale 16 Tesla dipoles, but that is a very reasonable technological path from where we are now. It is extremely unlikely if there's any insuperable check. We can already construct 16 Tesla dipoles. The only question is, can you make enough of them that don't blow up? And the answer is that's just an engineering problem that is completely soluble. So there are always, of course, possibly delays, but the longer timeline in the case of Europe is in some sense more guaranteed because the technology is less adventurous. Whereas absolutely the risk that's being taken in the US, we're not saying we should build the collider now, we're saying we should engage in the necessary R&D. If it succeeds, then we build the collider. If it doesn't, then indeed, we just have to wait till 2070. I don't know if that answers your question, but the point I wanted to convey is for the proton-proton machine, the technology is basically mature.
Can you also specify one thing? So JWST total budget is $10 billion. How much is that?
So the costing estimate in $2025 for a muon collider cited at Fermilab for a 3 TeV muon collider is between 7 and 12 billion. Okay, and then there's an upgrade to 10 TeV, which lives in the same ring. So at the end of the day, this is, of course, costing is always a dangerous thing. But the good thing in the US, a good consequence of the debacle of the superconducting super collider, is that we've gotten very good at costing accelerators because we know if we screw that bit up, we're dead. Right? So the 7 to 12 bit, that's a result that's produced not by people working on the muon collider, but by external panels convened to do costing estimates. So it's 7 to 12 with the 3 TeV version of it, and then the upgrade of magnets is another $3 billion to do 10 TeV. So it is ultimately a factor of 2 on JWST, but it is not out of scope of the sorts of experiments that we also propose to build with great merit in astrophysics and cosmology.
What are the assumptions on the R&D for that? Like, is that, is that optimistic? Like about
for the
cooling,
timeline.
example?
Yeah, so it's very
No,
clear
for
what
the
you
cost,
do.
for the cost.
So costing for the R&D is not the expensive bit, right? The expensive bit is really you still need a new tunnel, and you need the fast ramping magnets, and you need the dipoles for construction, and you
So like
need
cooling and things will just
the
be
4 megawatt power. Yeah. So the cost. So a good rule of thumb is a full demonstrator. It depends on how much of a demonstrator you want to build, but a full demonstrator for ionization, cooling, and fast ramping for a muon collider is in the hundreds of millions. Okay. So it is within the envelope of funding that currently goes to Duke, for example. It's not. The R&D is not the cost prohibitive.
Right.
Let's thank Nathaniel again.
Okay.
You can chat more with Nathaniel at the reception on the 8th floor.